Hello, welcome to the online course NICER 201 on causal inference from observational studies, CAUSIT. We are now into the second session of the topic p-values. In this session, we'll talk about how to interpret p-values. In order to go deeper into how to interpret, I'll make use of this example from Whitley and Ball's paper where they talked about hypothesis testing and p-values. So let's assume that the research question at hand is, in patients with acute myocardial infarction, does the administration of intravenous nitrate as compared to nothing reduce mortality? To answer this question, the most appropriate study design would be a randomized control trial, right? Where we compare acute MI patients who receive intravenous nitrate with those who do not receive the intravenous nitrate. And then we observe the effects, and here the outcome that we're interested in is mortality. And we look at what proportion of patients who were given intravenous nitrates had mortality, and compare that to proportion of patients who had mortality in the group where intravenous nitrate was not provided. Based on these results of the study, we need to interpret whether intravenous nitrate really influenced the mortality rates in the acute MI patients. Maybe there could be no real effect of intravenous nitrate on mortality, and whatever result that you see, whatever difference that we see in these two groups, maybe just due to chance, due to sampling variation, or maybe there may be a true effect of intravenous nitrate on reducing mortality. This is where we usually do the hypothesis testing. So the aim of hypothesis testing here would be to establish which of these explanations is most likely. We need to understand at the same time that statistical analysis can never prove the truth of a hypothesis, but it can only provide evidence to either support the hypothesis or refute. So these are results from 6 trials which have been done over time on the use of intravenous nitrates in acute MI patients. So we have trials by Kish, Busman, Flaherty, Jaffe, Liss, and Jagda over time. This table is a summary of the results from these 6 trials. The initial columns give you the 2 groups, intravenous nitrate group and the control group. We have the numerator, which is the number of people who died in each of these groups, divided by the number of people, the number of participants who were randomized to either the intravenous nitrate group or the control group. For example, in the Kish trial, 50 individuals were randomized to receive intravenous nitrate, 45 individuals were randomized to not receive intravenous nitrate. Out of these 50 who were randomized to receive intravenous nitrate, 3 died, and out of the 45 in the control group, 8 died. Similarly, for the other study. What these studies have calculated as a measure of association or causation between intravenous nitrate and mortality is odds ratio. There is the 95% confidence interval for each of these odds ratio and a p-value against each of these odds ratios. Now let us see how to interpret this measure of association. Here it is odds ratio between intravenous nitrate and the risk of dying among acute MI patients. For the time being, let us ignore the confidence intervals. What we can see here is that 5 of these 6 trials have odds ratios that are consistent with the protective effect of intravenous nitrate. As you can see here, their odds ratio is less than 1. In these 5 trials where the odds ratio is less than 1, in fact, the risk reduction ranges from 17% in the Flaherty trial to 76% in Busman trial. How did we get this 17% and 76%? Essentially 1 minus the odds ratio. So we could say that in the Busman trial, the risk of dying in the nitrate group is about 1/4 of that in the control group. Now we have one trial, the Jaffe trial, where the odds ratio is 2.04, which suggests that actually intravenous nitrate might be harmful. It is in fact doubling the likelihood of dying among patients who are given intravenous nitrate as compared to those in the control group. So now, how do we interpret the odds ratio based on the p-values? How do we use the p-values? The p-values are given in the last column of the table. They give an indication how likely it is that these odds ratios are simply due to chance or not. If you look at the p-value for the first trial, the Kish trial, it indicates that the probability of observing an odds ratio of 0.33 or more extreme, here more extreme would be less than 0. So it would be 0.3, 0.25, 0.2, and henceforth up to 0. If the null hypothesis is true, this probability would be 0.08. In other words, if actually there was no effect of intravenous nitrate on the mortality, which is our null hypothesis, right? The null hypothesis we state is that intravenous nitrate has no effect on the mortality of patients with AMI. So if actually the null hypothesis was true, then this 0.08 p-value would mean that 8 out of such 100 such studies would show a reduction in odds of 66% or more just by chance, right? Which is a pretty high level value. The p-value for the Busman trial, right, indicates that 1 in 100, it's 0.01. 1 in 100 trials would have an odds ratio of 0.24 or more extreme by chance alone. Now, this is a pretty smaller probability than the 0.08, but it may not necessarily alter clinical care in practice. In the Flaherty trial, we have a p-value of 0.70. This indicates or suggests we have an observed odds ratio of 0.83 is very likely due to chance because it is much closer to 1. So, having known this, how do we then make use of these p-values to infer about our research question? What is there a causal association between intravenous nitrate and preventing mortality among acute MI patients? For this purpose, we have to see things more than just the p-value. So whenever we are comparing p-values across different studies, apart from the p-value, we need to also consider the sample size of the study and, very importantly, what is the observed effect size. So here, if we look at the two trials, the LIST trial and the Jagdat trial, right at the bottom, the odds ratio in these two trials are pretty similar. You have 0.56 and 0.48, right? Both of which suggest that probably the risk of dying is half among patients who are given intravenous nitrate. However, you see that the p-value for the Jagdat trial is much smaller, 0.007, compared to p-value for the LIST trial, which is 0.29. Although the odds ratios are almost similar. Why is that so? Because mathematically, larger studies give rise to smaller p-values. Now, if we look at the Kish trial and the Flaherty, if we look at how many people were involved, what was the sample size of these two trials, if you can see that it was almost similar. So you had, in the Kish trial, you had 50 participants in the intravenous nitrate group and 45 in the control group. And similarly, in the Flaherty trial, you had 56 in the nitrate group and 48 in the control group. Pretty similar. But now here, odds ratio are very different. You have a much lower odds ratio of 0.33 in the Kish trial and a much higher odds ratio of 0.83 in the Flaherty trial, and also the p-values. The smaller p-value occurs in Kish study, which suggests that the effect of intravenous nitrate is much larger than that in the Flaherty study, which has a larger p-value. So more extreme effects, the larger the effect size, it is likely which will correspond to smaller p-values. Having understood this, we also need to be careful about some of the errors that we commonly make as investigators while interpreting p-values. Usually what we do, or many people do, is we divide based on p-value, based on a certain cutoff for p-value, we divide it into statistically significant or not significant. Usually this value is taken as 0.05. So p less than 0.05 is indicated as statistically significant. Should we assume that any result that is statistically significant is due to a real effect of an exposure on the outcome, that there is really a causal association between the exposure and outcome? Not necessarily. Even statistically significant results may be just by chance, because by definition, when we have 0.05, 1 in 20 comparisons where the null hypothesis is true will result in a p-value of less than 0.05. Again, statistically significant results may not necessarily be of any clinical importance. And we may get this statistically significant results even when we have studies with very large sample sizes, where if we do that, then even very small differences between the two groups, which may not really be of clinical significance or clinical importance or public health importance, may come out to be statistically significant, but that may not be of any use. We can also see that there may be potentially clinically important differences which are there, but because of the smaller size of the study, we may get p-values which are more than 0.05 and which is usually denoted as non-significant and ignored. We should not be doing this. In fact, it is better to actually examine what is known as the confidence intervals to come to a final conclusion about the study results rather than just depending on the p-values. P-values have certain limitations. When we make statements such as p less than 0.05, p more than 0.05, p significant, not significant, it actually does not convey much information about what the study findings are. And it's a very simplistic interpretation of our study findings. What would be good to do is to actually present the exact p-values. P is equal to 0.03, p is equal to 0.009, p is equal to 0.334, whatever, right? Now, presentation of such exact p-values allows the investigators to make an educated judgment to see whether the observed effect is likely to be due to chance and when taken into context of other available evidence. We can actually see it in the sort of the scale of going from 0 to 1 where the p-value is. And when we are comparing two studies, this can be much helpful. But we also need to understand that even if we have exact p-values, those p-values actually do not convey any information about the effect size. That is the size of the difference between the two groups or the strength of the association between the two groups. In fact, if you get a very small or very large p-value, it may be true or it could also be influenced by several other factors. This could be that it may not be clear whether the targeted hypothesis that we are putting up, is that really true or false? So even if the null hypothesis is not actually true, then we may not be able to infer anything based on the p-value. When we are doing studies, there can be violation of the study protocols in terms of inappropriate selection of study participants. There may be errors in data collection, there may be errors in data analysis. And so when we get results or in forms of p-values from such studies, they are not reliable. Finally, it is possible that investigators themselves, because of their own biased preferences, may present only selected p-values. So again, just depending on p-values for making an inference about a causal relationship between an exposure and an outcome is not desirable. Thank you.